Hello, and welcome to our webinar today. Our title is Machine Learning and Statistics, Similarities and Differences. It's brought to you by ASQ's Statistics Division. Our speaker today is Alex Gutman, who is a data scientist and a corporate trainer and an accredited professional statistician. He's also author of the book, Becoming a Data Head, How to Think, Speak, and Understand Data Science, Statistics, and Machine Learning. He's an adjunct professor at the Air Force Institute of Technology, and in 2019 received a Fulbright Specialist grant to teach data science and machine learning in Kyrgyzstan. So I think we have a great webinar for you today. A couple things. If you have questions throughout the talk, feel free to ask them in the chat, and we will read those off at the end of the session. Also, if you have any technical difficulties, you can do the same thing, and I will try to help you. With that, I will hand it over to Alex, and we'll get started.
Thank you. Thank you, everybody, for joining this call, and thanks to the Statistics Division for the invite to talk about machine learning and statistics. So our agenda today, my disclaimer is that today is not going to end decades of debate. The machine learning and statistics, it's often viewed as a political debate where one's almost meant to take sides. So my goal is to kind of give everyone an understanding of the different viewpoints on each subject, where they are similar, where they are different, and we're going to do that by going through a scenario and maybe talk about how a machine learning engineer might approach it versus a statistician. I'll have a few definitions, highlight differences and similarities, and with the differences, there are always going to be exceptions, so we'll speak very broadly about the differences. And also towards the end, I want to talk about deep learning, which is a part of machine learning that is driving, I'm sure, a lot of the hype that you hear today. If your company or manager is often talking about machine learning or AI, a lot of that is driven by this subfield called deep learning. So I just want to highlight what that is and how it fits into this picture with statistics and machine learning. I did have an introduction, and thank you for that. I just wanted to put this up here real quickly because when talking about machine learning and statistics, I think it depends on the view of the presenter. So I have my background here. My background is in math and statistics, and during my career at Procter & Gamble and then 8451, and which is owned by Kroger, I moved a little bit from inferential statistics more into machine learning, and I'll talk about what that means. I do have P&G here at the end because I'm actually returning to P&G. But I view statistics, machine learning, this whole space is very exciting to me. So I'm not trying to put someone on one side of the scale that it's machine learning or statistics or AI. The titles matter less to me as I'm moving on in my career because there are so many interesting problems to solve, and I hope I can convey that to everyone on the call. Okay, so I want to start with a scenario with some example data here where you have information about some apartments in New York City, number of bedrooms, number of bathrooms, the size, location, and then the sales price. So a scenario might be, okay, take this data. Now, imagine we have several thousand observations, not just the 3 I have here. But what would you think to apply? Would you think, okay, this is a statistics problem or this is a machine learning problem, maybe both? So I know we're not taking a poll or anything, but just kind of think about this question here. And as I said earlier, this statistics and machine learning are often viewed as opposing sides, where there's often this versus, as opposed to what I like to view as an and, statistics and machine learning. So I'll just restate that I'm not trying to put anyone on to tip the scales towards statistics or machine learning. but I just want to make you aware of what the debate has been and then leave you with an appreciation. Now, the usual jokes, I'm leading off with this because many on the call have probably heard some of the jokes about statistics and machine learning, where a machine learning engineer is a statistician with a Mac, or machine learning is glorified statistics. And then the last one, whatever machine learning is, statisticians will say that they did it earlier and better. I don't want this to be, my talk to be further banter for this. I'm saying this because a lot of us on the call have heard this, at least some of my professional colleagues. You know, we would hear similar jokes. So the bottom line is that statistics and machine learning, they use similar tools and methods. One is not better than the other. The difference is really in their strategies and what they emphasize. And that's going to be the bulk of this presentation, is saying what statisticians emphasize versus machine learning engineers. And the goal is to leave you with an understanding and appreciation for both methods. Okay, let's start with some formal definitions, and I know definitions aren't always the most entertaining place to start. We can look these up on Wikipedia, but just to have a starting point, we'll define machine learning as computers that can learn tasks without being programmed. I'll have a slide to explain this a little bit. This machine learning grew out of computer science, is considered a subfield of artificial intelligence. Statistics, and I imagine most people on the call, being that this is hosted by the Statistics Division and part of ASQ, I assume have some familiarity and background with statistics, but that's the collection, analysis, and explanation and presentation of data, which is grew off as a branch of mathematics. And I want to return to this definition of machine learning, this idea that the computers can learn tasks without being explicitly programmed. This slide was helpful to me trying to think through this. So a normal computer program, you might have some inputs, and then a computer programmer would come up with some rules to convert those inputs into an output. And the idea of machine learning is to flip this, where the outputs go into the code, and some machine learning algorithm comes up with what they call as a learning program. So to make this a little clearer, let's walk through with that data set I shared earlier. So an input, if your goal is to predict the sales price of a home in Manhattan, might be to take some inputs, bedrooms, bathroom size, location, and the traditional way may be to develop some rules. If there are more than 2 bedrooms, then increase the price by X. If there's only 1 bathroom, then decrease the price by Y. So a traditional program would have all these handwritten rules, and these could get very lengthy and confusing, but maybe at the end you end up with something useful, an estimated listing price. So this might be subject matter expertise in forming a computer program. The idea of machine learning is to take data, both the inputs on the left and the outputs on the right, and feed that into some type of learning algorithm to develop a model or an equation that would take as an input the number of bathrooms, bedroom size, location of a new apartment, and predict an output. So this is historically was like the motivation for machine learning, is to take the data and let it kind of write a program by itself. Now, meanwhile, statistics have had tools that could do this for years. We have regression that can take as inputs and map outputs. So a lot of the tools were kind of inherited by machine learning as they were trying to go about their goal of making accurate predictions on new data. So I wanted to provide that additional context to machine learning. And now we're going to go back to this relationship and walk through how a statistician might deal with this problem versus a machine learning engineer. So here's our data set. And the question here is very vague, model this relationship. And this is where some of the differences start to matter between the two. Because if you're a statistician, and like I said in my background, I am a statistician by training. So the first step that we often learn is, well, let's assume that the data is generated, there's some truth in the world that we are trying to model. So in statistics, we often hypothesize a model. We're going to say that the sales price is some function of beds, bath, size, location, plus this epsilon, plus some unknown error term. And many times we start with a linear equation where sales is going to equal some base price plus some number times the number of beds plus a different number times the number of baths, etc. So the key is that we're starting with a model. We're assuming that the relationship can be modeled with this particular form, and then we use our statistical methods to estimate what these numbers might be, these beta terms. Then we go through some statistical tests where does the data fit the model? Are any of these parameters significant? For example, does location matter? Otherwise, could this coefficient be a 0 or not? So we do different hypothesis testing. And when we have that model, we may be able to answer certain questions as, on average, how much does an additional square foot add to the sales price? Now contrast this with the way a machine learning engineer might frame the problem, where their emphasis is mostly on prediction. How well can I predict the sales price of data that I have not seen before? So a machine learning engineer will say, okay, sales is a function of these things, but I don't know what the function is. So we're not going to assume by default that it's a linear equation or some other framework like this. They may not even care what that function is. They're just trying to get this prediction machine that'll take an input and provide an output. Now, the regression model that I shared on the previous slide may be one of many types of models that a machine learning engineer tries. And they end up picking the best one on what's known as a test set. So I'm going to move on to this slide and explain with machine learning. Well, first with statistics, when we have a data set, so we have labeled observations, so these could be every row has all this information about a house as well as a prediction. With many statistical modeling techniques, we just fit a model to the entire data set because we're trying to understand these relationships, and maybe we get some predictions as a byproduct. But with machine learning, prediction is often the #1 goal. So they withhold part of that data, which is called a test set, and lock that away for a second. That's going to be representative of data that we haven't collected yet. So then they fit a model on this training set using a machine learner, but again, this could be any type of algorithm or model. And then once that model is generated, we score, we would say hold back thousands of apartments and see how well the model did predicting what the real price was and collect a few statistics on that. So the general differences, to summarize what we've covered so far, and just quickly in the last 10 minutes or so, is in machine learning, there's not really this assumption of a model in the sense that as a statistician we often assume, where we assume a model that there's some data generating mechanism that has a specific form, and then we fit the data to that model. And after we do that, we'll run our analysis. Is the model appropriate? Is it meeting our assumptions of that modeling framework? Are the variables significant or not? And then we can use that model for inference or prediction. Whereas machine learning, the main idea or the main goal is to have some model, whatever form that looks like, that can perform well on unseen data, data it has not seen before. So a machine learning engineer might try several different methods. And then whichever one performs the best on a test set, then that's the one that they go with, and that will be put into production. So similar methods, and we'll discuss how we're borrowing from each other's toolkits here, but a different emphasis, right? On the right, it's really about understanding and inference and decisions, and on the left, it's really about predictions. There are some other differences too, as what about correlated data? As statisticians, my entire dissertation research was on collecting data that's as uncorrelated as possible, because correlated data can negatively impact your predictions from any model. So we worry a lot about testing the data. If two variables are correlated, maybe we pick one over the other. And we worry about confounding, because any correlation, confounding, any messiness in the data can really impact our understanding of the relationships from the inputs to the outputs. Whereas machine learning, because you're only focused on prediction, well, I say only, but often focused on prediction, correlated data can sometimes help. It's often described as it's not a bug in machine learning, it's a feature, because maybe there's some other information that's collected that improves your predictive performance a little bit. So in statistics, we often focus on collecting uncorrelated, non-confounding data. And machine learning, there's probably less of a concern about correlated data, but a focus on getting more data. So statistics, cleaner data; machine learning, more data. And then there are different types of questions that you can answer. Machine learning, you're going to ask, how much can I expect to pay for a 3-bed, 2-bath, 1,500 square foot in the Bronx? And statistics, you might think to answer, on average, how much does an additional square foot add to the price? Or what's the expected price increase if I move to Manhattan? So if you think in terms of the questions that you're answering, one difference that's often pointed out between machine learning and statistics is relative to the outcome of the process. The outcome of machine learning is often a piece of software. Machine learning engineers will build a model, and then it's what they're really building is this computer code that could then be, for example, put on a website. We're dealing with real estate prices here in this example. So the piece of software may be a predictive model that is put out for all of us to use on Zillow. I'm sure many of us have gone to Zillow and looked at our Zestimate of our sales price. This is not my home. I was curious to see what the Zestimate was of the White House. But you could all go to Zillow and look up the cost. And behind the scenes, you have a model that's making this prediction for you. On the statistics side, the outcome can be software. Again, there are exceptions to all of these, but the outcome is often in the form of a decision. It's a piece of paper, it's a presentation, right? What is the impact of poor schools on sales price? Is a newer kitchen worth the investment? So similar tools can drive both of these, but there's a different emphasis between machine learning and statistics. Okay, moving on in terms of some of the practical differences that you might see. In machine learning, if people who program often use the language Python, whereas in statistics, it's often in the language R. Many statisticians still use SAS, but R is becoming more popular as it's open source and free to use, as is Python. There are other tools that you may use to do your own statistics. JUMP is a point-and-click tool, as well as Minitab. And on the machine learning side, there are other tools being developed. One is DataRobot that builds multiple models for you. So the tooling is a little different. But of course, you can do a lot of machine learning in R and you can do a lot of statistics in Python. So it's not a clean separation as I'm presenting here, but people coming out of schools, statisticians may not know Python, and machine learning engineers may not know R. Now, some companies do their best to try to educate new employees so that you know one language really well and kind of know the other one. But coming out of school, this tends to be the case, where stats knows R, machine learning would know Python. With data sizes, I mentioned how machine learning generally uses larger data sets, and that's not to say that statistics does not work with large data. Statistics does work with large data, absolutely. Statistics is also very helpful with small data, but machine learning is not. Machine learning, in order to make accurate predictions, you need enough data to split your data set into these train and test splits. If you only had 20 apartments to learn from to predict the sales price in Manhattan, you're not going to be very confident in your predictions. You may be able to collect some interesting statistics on the data you do have, but in order to have a really accurate predictive model, you need to have more data. In fact, I went on the website for this Python library called scikit-learn. This is Python's a computer language, and scikit-learn's a library that allows people to do machine learning algorithms very quickly, just a few lines of code. And it gives you this flow chart where you can see, okay, what type of model should you use based on what type of problem you're working with. And I want to zoom in on the first decision that it asks you to do. Do you have less than 50 samples? If you don't, get more data. And as a statistician, I've had several problems where I would have loved to have 49 samples, because that would have been, some of the data as a statistician that we deal with is very expensive to collect. There's an entire field around this called design of experiments, which is about collecting limited data in the best possible way. But when the goal is prediction, you want to have more data because you want to be able to be confident that your predictions are going to be accurate. So this is, I think, a differentiator that people often make between statistics and machine learning. All right, so we discussed some differences, but there are similarities. Both ultimately deal with understanding data. And regardless of whether you're building a predictive model or doing some statistical inference, you want to have accurate, relevant, and enough data. The underlying data matters. Many of us have heard the mantra, garbage in, garbage out. An analogy I like to use with managers is that the data is to ingredients as a model is to a meal. So if you have bad data, you're going to end up with a bad model. Just as if you had bad ingredients when you're cooking, you're going to end up with a bad meal. The other point I make when sharing this analogy is that if you have bad ingredients while you're cooking, it doesn't matter if you're a 5-star chef. The meal is going to be terrible. So this is a misconception that I try, and maybe some of you on the call have dealt with this, is that your data may not be clean, it may be messy, but maybe you've heard, well, try some machine learning method to see if it works. But the latest and greatest methods aren't going to save you from bad data. The underlying data matters whether you're doing machine learning or statistics. So this is an important thing that we all know to be true. I think some companies and others would like this, we'd like to think, well, if the data is okay and I have some latest and greatest method, it's all going to work out, but that's not going to be the case. Both machine learning and statistics share common pitfalls. These shouldn't be a surprise, because my intent is to show you how much we overlap. You always need a specific question to ask, whether you're doing prediction or explanation. you don't want to solve the wrong problem. There's always questions about data. Can you get the right data you need for the problem? And does the data contain the information that you thought it contains? A machine learning engineer working at Google or a statistician at Procter & Gamble would likely tell you that they spend a lot of their time dealing with messy data. This can come in different forms. I've had one case when I worked for the Air Force where I just had data spread out across dozens of spreadsheets, multiple zip folders, different worksheets, very messy. And that's different than someone at Google who may be trying to wrangle billions of lines of, billions of observations spread across multiple clusters. So different, the same theme, right, but maybe different types of messiness. Whether we're doing stats or machine learning, we don't want to force a solution where one doesn't exist. Both cases, with the hype around data science, statistics, machine learning, there's inflated expectations of value, where it's often assumed that, you know, with data you can rule the world. But I think we know that not to be true. You need to have accurate data to get anything useful. Another pitfall is overkill. So on the statistics side, maybe we're modeling a relationship and we make it too complicated. And one thing I remember learning in many statistics classes is, you know, Occam's razor: keep it simple. Don't make anything more complicated than it needs to be. On the machine learning side, I'm a machine learning practitioner as well as a statistician. Overkill I see a lot, where people are trying these very complicated models, tweaking all these bells and whistles when a simpler model would often be fine. So overkill is a common pitfall that I've seen in my experience. Okay. Another similarity is just this idea of supervised learning. Supervised learning is, you might hear it called different things, but it's just the idea of taking inputs and mapping them to outputs. So the features of a house are your input. The output might be the sales price. The input to a different supervised learning model might be the picture of your face, say if you own an iPhone 10, and the output is a question, yes or no. Is this you? Will it unlock your phone? Another one is an email message. There's a prediction if it's spam or not spam, 0 for no, 1 for yes. In statistics, we might call these problems regression problems if we're predicting a number, like sales price, or classification problems, where we're predicting a category, where we really predict a probability. So whichever way you phrase this, right, you have inputs, you may call them independent variables, and then over here you have a dependent variable. You have machine learning engineers often use the term feature instead of variable, predictor, covariate. There's so many different terms to learn, and I think that's where some of the confusion lies. But different terms are describing the same things here. But what's similar is that these algorithms that are used by statisticians and by machine learning engineers are all very similar. Like, how do we get to that model? Well, you can apply linear regression, which I shared an example earlier. You could do logistic regression if you need to predict the probability. You could do classification and regression trees, random forests, many others. And these are shared methods developed by statisticians, some with tweaks from machine learning engineers, but it's all part of this broader toolkit. Now, some of these methods are better for explanations, and others are better for predictions. So now I'm going to highlight a different example and show and discuss logistic regression, trees, and random forests, and explain what each of them offers. So here's a data set, this data that I made up, where you have, imagine we're a big company and we're hiring summer interns, so we get data from previous interns on their resume, what was their GPA, what year in school, what's their major, computer science, econ, stats or business, how many extracurriculars are they in, and did they get an offer, yes or no. So this is a classification problem because we're predicting a 0 or 1, no being 0, yes being 1. With logistic regression, this may be your approach starting, whether you're a machine learning engineer or a statistician, but you're coming in with an assumed model. We're saying, well, I think the probability can be modeled by this equation. Now here I only have GPA, but the math behind the scenes filled in these numbers here. We have an equation, and as a statistician, I may be interested in how much does GPA matter if I controlled for all the other variables. I'd have to model them up here, but another thing statisticians are often interested in that a lot of machine learning methods can't provide, or some of the other methods I'm about to share, would be prediction intervals. So someone with a 3.8 GPA, maybe their point estimate's a 0.8 probability of an offer, but the prediction interval is 0.7 to 0.9. Prediction intervals are very helpful to have. And these are statistics questions because we're concerned about interpretability and uncertainty. Now, trees they offer some interpretability. So you could, seeing this model, you could say, well, if the student has less than a 3 GPA, but is in more than 4 extracurriculars and majored in computer science, then yes, I would predict that that person would receive an offer. But there's no assumed model behind the scenes with the tree. And that's one of the big differences between stats and like assuming a model as we often do, between statistics where we assume a model and some other methods where we don't. The data just kind of figuring out, we let this tree-based structure kind of partition the data in meaningful ways. This can get more complicated. Now, trees are an old method. It can get more robust and better predictions with what are known as a random forest, where you build several trees on samples of the data, or sometimes it'll split you by major first. Down here it's GPA again. Over here is the number of extracurricular activities. So if you, as an applicant, you would go through, here I only have 4 trees, but you go through hundreds of trees, and the final prediction would be a majority vote. Trees have shown that they're created in 2001 by a statistician, but it's often considered a machine learning method because the predictions are so good out of these. Random forests often win machine learning competitions. The downside is that they do get harder to interpret. One tree is hard enough. Now imagine 500 different trees. Then it becomes harder to assess some of these statistical questions that we're after, right? Like, how much does my probability increase if I study really hard next semester and raise my GPA by 0.2. So in terms of this interpretability and predictive performance, there's a trade-off where linear regression models are very interpretable, assuming that the data underneath is uncorrelated. Decision trees are are somewhat interpretable, but sometimes they get better performance accuracy. Then as you go down, random forests, less interpretable, better performance, and then neural networks. I'm not going to cover support vector machines. But this is a trade-off where sometimes statisticians may want to live in this quadrant here because the interpretation is so important. Like, you will sacrifice predictive performance as long as you can understand what's going on. Whereas a machine learning engineer may not care what's going on, but they just want to eke out predictive performance. And that leads to one of the big opportunities in machine learning is how can you have the best of both worlds? How can you have a model that predicts well, but is also easy to understand? Many people will consider machine learning to be a black box. And in some cases, that's often very true. And as more models are made with machine learning, I think it's going to become very important to understand what's going on. a lot of car insurance companies are saying, you know, drive with our app turned on so we can learn how you drive. That's going to impact your premiums for auto insurance. And if your premiums go up, I'm sure you're going to want to know why that happened. But with some models, it's often very hard to do. So from the interpretability standpoint, these are all reasons that we want to understand what's going on. But it's that trade-off. Do you want better predictions where you don't know what's going on, or more interpretable where you sacrifice predictions? So there is active research in this area called interpretable machine learning. Okay, now I want to move into deep learning, which is a subset of machine learning that's really driving a lot of the hype that, you know, maybe it led you to this talk, or maybe you've had conversations where you've heard about AI and deep learning. So I wanted to communicate where that comes in and also talk about unstructured data. Now, a lot of this hype is deserved, in my opinion, and I think you'll agree with me once you see some of these applications. So first, a bit of a history. So there's this graphic's from NVIDIA. There are 2 points to this graphic. One is that artificial intelligence as a field has been around for a very long time. It's been around, you know, not as old as statistics, right? But it's been around since the 1950s. And how can we get computers to think like humans? Now, machine learning is a subset of artificial intelligence. So that's the first point of this graph, is there's a Venn diagram. Machine learning is a subset of AI. Now, in the 80s, machine learning engineers, they started to apply some of these statistical methods. They're getting very good predictions. They start making tweaks. So this is where a lot of the overlap, and I think some of the political debates come into place, because machine learning engineers are using statistical methods, and it's kind of like who invented what, who gets credit. But there's still a lot of great progress being made in terms of like mailing letters and reading zip codes on your mail. In 2010, when more data became available, larger data sets and bigger computers, a subset of machine learning called deep learning really started to become popular with unstructured data sets. So what are unstructured data sets first? Most of the data we deal with is in this very structured form, rows and columns. It's in an Excel spreadsheet. It's in a database. Unstructured data would be text, audio, and images. So text is inherently unstructured. It's messy. And part of machine learning and some of the research is, okay, how do I get this unstructured data into a structural framework that I can analyze? So one easy way to do it is, so if you're trying to assess whether this tweet is positive or negative to Kroger, this first one's negative. Someone's upset, and you flag keywords. The word Kroger does not appear. The word refused appears. Great appears. Does not appear, but great appears over in this one. So it's how do you take this unstructured data and put it into a structure? So there's a lot of thought that goes into this. Images fit this framework as well. So if you have an image, it's broken up, and it's not a clean spreadsheet. It's more of like a cube where you have a red channel, a green channel, and a blue channel. So for every pixel, you have a dot. It's the amount of red, green, and blue that's in it. So this would be the input. Now, how to get to this unstructured to the structured data set, this is where a lot of research has gone on in machine learning. One thing being, it's called convolutional neural networks. And my point of showing this to you is that it's to caution us to be dismissive of machine learning. You know, I don't think it's fair to say machine learning is just glorified statistics, because researchers in machine learning and computer vision have been doing tremendous things with image analysis that are driving huge impacts on our daily lives. So you can kind of think of convolution as a magnifying glass going over these pixels, and it's, you know, some math on these pixel values that identifies edges, curves, diagonals, textures, goes through an equation, a neural network, and makes a prediction. And deep learning is the reason why people can look into their iPhone and it'll unlock by looking at your face. It will do speech translation. Deep learning models have really improved the ability to go to English to over 100 other languages on Google. There's augmented reality, where you can, if you're traveling internationally and take a picture, it will use a model to translate this text into English. And deep learning also drives or helps drive self-driving cars. So the hype around deep learning, a lot of it is warranted. I think as a practicing statistician and machine learning engineer is that when deep learning is posed as a solution to every problem, which it's not. It can solve a lot of great problems, but not every problem. So some of the pushback is also warranted because I've been in rooms where someone thinks deep learning is an oracle, like have a hard problem, deep learning will solve it, but that is not true. We have to think back to the garbage in, garbage out, good quality data. For deep learning to work, you also need enough data. So this is saying like on small data sizes, you kind of have traditional machine learning, statistical learning algorithms. You can think regression and maybe some trees here. For small data, these tend to work pretty well. There's just not a lot of data for some of these neural networks to work. But as data gets larger, and this has been true particularly with unstructured data like images, neural networks eventually surpass, say, a regression model and start to get really accurate in terms of model performance, which is why a car driving down the road can identify a tree, a stop sign, a bike, etc. But for small data, you know, we still have our tried and true methods that won't go away. And they shouldn't go away because they offer some interpretability. Now, with these improved predictions comes this black box rearing its head again, where decisions are being made, but there's not always an understanding of why certain decisions are being made until maybe it's too late. So here's an example where Amazon trained a model that reviewed resumes, and you know, there wasn't a nice simple regression that would say had a coefficient in front of male or female saying if the model was biased or not. It was this big complicated black box. But when they looked into it, the model was just reinforcing decisions that Amazon has been making for years, which was that it hires more men than women. The model just encoded that bias. But because it was so complicated, it wasn't as interpretable, and no one could do like a statistical analysis on it until well after the fact. This is a popular one you may have seen on Twitter. This is a Tesla that keeps spotting all these traffic lights. And it was just driving behind a truck with traffic lights. So this is where the black box can rear its head. Like, how well will deep learning models do with these edge cases? So that's why interpretation still very much matters. All right, so just to summarize in the last few minutes, these are very broad generalizations. But in terms of the emphasis, machine learning is prediction accuracy on data you don't have. That's what machine learning engineers care about. Statisticians will really emphasize formal statistical inference and understanding of the data that you do have. Stats is on large and small data sets. Machine learning has to generally pass some threshold for you to be able to do anything with it. Some of the more practical considerations that I've seen where I met people going through machine learning programs are generally educated in the computer science department as opposed to a statistician like myself who's educated in the math and stat department and learned R. They often learn Python. Their products often software. Ours would be papers and recommendations, decisions. They're often interested in how will this scale, right? I have a model that predicts homes. How can I make it predict homes in every zip code across the US? Statisticians are often trying to think, how do I quantify uncertainty? Now, even within statistics, we have our own infighting. You know, early on, I said this shouldn't be machine learning versus statistics, but even within statistics, there are frequentists and Bayesian, so we just can't escape. As you go down these subfields, there's always these fights. In machine learning, there's a lot of discussions now on the ethics of machine learning models and their interpretability. This was a fun chart. Rob Tibshirani, who is a statistician who does a lot of statistical learning, which essentially is machine learning, talking about the different terms that are used, like a machine learning, where a statistician might say fitting, supervised learning instead of regression classification. A large grant for machine learning is $1 million. A large grant for a statistician is $50,000. And then this would be a conference. Nice place to have a meeting in the French Alps for statisticians, Las Vegas in August. All right, so where did we land after all that? I think it's important as practitioners to speak both languages, be familiar with how machine learning engineers reference data, because it is different, what we call independent variables, they call features. Our clients, managers, and business partners, they've heard the hype around machine learning, and I think that's where a lot of the frustrations come in as a statistician, where our knowledge as a statistician should be to help, we should be able to help them navigate. They should trust us to use the right tool for the question at hand. So I felt this as well. I know others have felt it, and I think that's why there's this bit of, there's this fighting with machine learning and statistics. But I think the way to get around it is just to broaden your toolkit, learn a bit from both fields, understand the contributions, and apply the best method when you can. And also, deep learning, if you hear about it, does have a lot of hype, but much of it is very warranted. Have a few papers to read, and I can share these slides if anyone's interested. But these are two common two papers I reference a lot in this talk, to explain or predict, which you heard me repeat ad nauseum during this talk, and the two cultures of statistical modeling. One is where you specify the form of the equation, like in regression, and the other one is when you kind of apply a general algorithm like a tree to figure it out. And Leo Breiman, he's the one that is responsible for some classification and regression trees as well as random forests. All right, thank you all. That concludes the talk. Ended it with a little joke. Machine learning algorithm walks into a bar. The bartender asks, "What do you have?" The algorithm says, "What's everyone else having?" And if you're interested in learning more about this space, please check out my book. We have a nice chapter on deep learning and text and some analogies to help understand random forest and some other algorithms. The book is really meant for people who work with statisticians and data scientists who have kind of heard the hype, but need some training in how to understand statistics, probability, prediction. But I think many on this call would enjoy it as well. All right, thank you.
Okay, we have several questions if you're up for that.
Yes.
One of the questions was about the data set. When you have a data set and you're going to do machine learning of some sort, how do you decide what is in the test data set versus the training data set?
It depends on the type of problem. So if you're doing a regression problem where you're predicting a number, you would take a random sample. That's also why you need a lot of data. But general rule of thumb is that 20% of your data you're going to hold out as your test set. Now, if you're doing a classification problem, you want to do stratified sampling. So say you're predicting disease prevalence, or where, let's do COVID, because that's, right? Maybe 15% of the people in the data set have had COVID, and you're doing some algorithmic test. you would want to make sure your test set represents that 15 to 85 split of the entire data set. You do it randomly, but a stratified random sample.
Great. Do neural networks relate to statistics at all?
Yes. So a basic neural network is essentially, could be a logistic regression model. If you have a more complicated neural network, it's like a logistic regression model of several logistic regression models. I could give a whole talk on this, but yeah, neural networks definitely relate to statistics. Neural networks are actually quite old, but they kind of fell out of favor for a while until the computers became fast enough to figure out all these different parameters involved. But yeah, you could think of, you could model basic logistic regression as a neural network if you would like.
Tesla's using neural networks to establish their self-driving, but it sounds like they're not very interpretable, so we may not know exactly how it works. So what do you think of that system?
Yes, that is the big challenge that's going on, which is why more research is being geared towards understanding these deep learning models, because as humans, we're very good at recognizing edge cases. So say you're driving down the street and someone's waving their hand at you. Maybe it's a neighbor, maybe it's a hitchhiker, whatever. Those are easy for us as humans to understand, hard for a neural network. I mean, number one, you need a lot of data. And then two, when the car makes a decision, how do you track down why it made a certain decision? There's going to be legal ramifications for this. I don't have the answers, but that question is why I think it'll be a while until we have fully automated self-driving cars. There are just too many questions, both legally and these edge cases, to figure out. Thanks.
How are the trees in random forests created? Are there probabilities included, or are they just 0-1 results?
The output can be a probability with trees. So I can actually, let me see if I can go back real quickly to that first tree. So there are probabilities that can be involved. So if like students have below a 3 GPA and we're in fewer than 4 extracurriculars, this 0.2 is saying that 2% of the people that met those qualifications fell into this bucket, or sorry, only 2% of the people who fell into this bucket were admitted. So yeah, the output could be a probability. Like whereas over here, you would give a 0.14 chance to anyone who met this qualification. So the output can be a probability. The decision threshold comes later, where you as a statistician or you have to meet with stakeholders to understand where do you want to set the threshold. If anyone has above a 50%, should we accept or reject? But yes, the short answer is that yes, it can output a probability.
Thanks. Is there a risk of machine learning exacerbating market trends, like the housing market?
That's a good question. I mean, I think so, because eventually it can become a reinforcement, right? It's self-fulfilling. Prices have been rising. It's predicting future prices, which becomes, then people think their homes are worth more. So yes, I think that's true with that would be true with like a statistical time series model as well, where we expect the trends that exist at this moment to perpetuate into the future. But as we know, that can come falling down hard quickly. Like every model, you know, I was working at Kroger during March of 2020. Every model we had was essentially useless because the world changed. Every trend dropped. You know, no one could predict toilet paper was going to skyrocket like it did. Yeah, so we have to be very careful about this feedback loop where we assume that what happens from a model becomes reality. Yeah, that's a good question.
When selecting data for machine learning, is there any need to check for normality?
Generally, that is not concerned at all, because a lot of the models don't assume that the data was generated from that it's conditionally normal in any way. So if the data, that may be a check people do on the back end, but in general, there are not many statistical tests done on the data. I'm not saying there shouldn't be, but in practice, a lot of people don't do that.
How easy is it to comprehend the machine learning and AI without a lot of background in some of the languages like Python and R?
It depends on what degree of understanding you're after. Now, part of the reason, that shameless self-promotion of my book, right, is that I wanted to describe, to give people like a mental model of what's going on without having to code or understand a bunch of math. So I think you can learn enough about some of these methods in order to challenge them and speak intelligently about them, whether you program them or not. Because at their core, the challenges, when it was going through the similarities, the challenges that these methods face are the challenges that we are always going to face as people working with data. Is the data sampled appropriately? Does it measure what we want it to measure? So regardless of algorithm, you can still speak intelligently about these just by focusing on the data and how it was collected.
Are the deep learning black box models considered more reliable for prediction now than standard traditional statistical models?
Yes. Yeah. Deep learning model for large data sets, especially on images, deep learning models have just made substantial improvements, especially with images. Like if anyone was a Facebook user, used to click on your face when you were tagging pictures way back when, enough data was labeled that now a deep learning model can just pull up a picture and it says, okay, that's John, that's Sally, etc. And that's all because of deep learning and its substantial improvement with unstructured data. I will say with structured data, rows and columns and spreadsheets, I should have had a slide on this actually, deep learning is often overkill if you just have regular spreadsheet type data and database data. Trees often work just as well as deep learning. Deep learning works really well when you get into text, audio, and images.
Great, thanks so much. I think we covered all the questions we had so far. So that was a wonderful talk, and we'll be posting that on the YouTube web channel that we have in the next couple of days. And I really appreciate the talk, Alex. That was really good. Thanks so much.
Thank you. Thanks, everyone.